So now let's look at the Laplace transform of the real exponential. Now the exponential is going to be this function here, e to the at, so it's a real exponential because a is a real number. So to find the Laplace transform, we've got f of s is integral from 0 to infinity of our function e to the at times e to the minus st by dt. So that's integral from 0 to infinity of e to the minus s minus a of t by dt. Now we can go ahead and we can integrate this, in which case you would have minus 1 upon s minus a times e to the minus s minus at all from 0 to infinity, and you could put your values in for 0 infinity and you get 1 upon s minus a. Or we can just quite simply note that whenever we did the Laplace transform of e to the minus st, we got 1 upon s, but now we don't have e to the minus st, it's s minus a, so you really could replace the 1 upon s with the 1 upon s minus a. Okay, so it just means that in order to get the Laplace transform here, we're really just taking this exponent that's inside that bracket. Okay, so it's going to be 1 upon s minus a. So I suggest if you're unsure, you just try multiplying those out and doing that integration. So therefore we can say that the Laplace transform of the real exponential e to the at is 1 upon s minus a. But what about the region of convergence? Well, now the region of convergence is the real part of s greater than a. Now we'll be able to see that just in a second. So if we noted that we get a pole whenever the denominator is equal to 0, so by a pole I mean a point of infinity, so whenever the bottom line of this is 0, this whole thing is equal to infinity. So the question now is, what makes the bottom line equal 0? Well, we just put the values in, so s minus a would have to equal 0 in order for there to be a pole. So the pole must exist at s equals a. So it means now that we've got a method of choosing whereabouts along this sigma axis the pole is now going to exist. So in this instance here, the pole is going to exist whenever sigma equals a. So let's say, for example, we have a sigma and a j omega axis. Now we can position that pole anywhere along this axis. So for example, if a was a negative value, it would be along at this side of the axis. So it means that we can ensure that the Laplace transform will converge for all values, well, real value of s greater than a. So really what we're saying is the sigma value is greater than a, then everything in that area there will converge. Of course, everything to the left of it will still diverge. Okay, there won't be any convergence. So that shows us that the point of multiplying or finding the Laplace transform and multiplying with the real exponential is that the real exponential allows us to shift this pole up and down the sigma axis, which is a very useful thing to do, which we'll go into in another video. So we can see why it is that we're able to get that extra bit of region of convergence by multiplication by e to the at. Because if we looked at the Laplace transform, let's say we take the Laplace transform of e to the at here, then we know that we're going to multiply that by e to the minus sigma naught t. So that's one particular value of this e to the minus sigma t surface. And then this will give us a final value here, which will then go and will modulate the cos and sine omega t surfaces and will generate the imaginary and the real part and then the magnitude of one slice of the Laplace surface. But we can see that in order to build up the entire surface, what happens with this function here is that as it slides back further here, then it starts to become closer and closer to just a little square function. So for example, whenever this goes back to the point where the sigma is equal to 0, you just get e to the 0, which is a value of 1, so you just don't have a straight line here. And then this side of the axis, it's no longer going to converge, it's going to start to diverge. Okay, so we're going to have the scenario whereby we'll be multiplying this function here with this function here, and you can see then that we're going to have a trade-off between how quickly this converges and how quickly, say, this one here was to, how quickly this one converges and how much this function here diverges at this side of the graph. Okay, so there will be a particular point where the convergence of this one and the divergence of this one will exactly equal each other, and we would just have a value of 1, but that's now going to occur not at this point here at 0, it's going to occur somewhere along this axis dependent on this value of your A. So that gives an indication of where we get the extra region of convergence. So let's look at this Laplace transform graphically in Matlab. Now these are the outputs from Matlab. After we've looked at the outputs, we'll go ahead and we'll look at it actually producing live values in Matlab. So we're taking a function we wish to find the Laplace transform. So we want to find the Laplace transform of the e to the, say, minus t. So in this case here, the value of a is minus 1. So let's say that we're going to work out the Laplace transform. So we're going to multiply that by some value e to the minus sigma t. So let's say this sigma is actually a value of minus 2. So we have e to the minus t and e to the minus 2t. So that means that when we multiply these together, this one particular surface is going to be e to the minus t times e to the minus 2t. So let's go and we'll see what happens when we take this surface here. So we take this function here and we let it modulate the cos omega t and the sin omega t surfaces. So this is the function here, e to the minus t, which has been modulated by e to the minus 2t. And this here is going to modulate the cos omega t surface. So we can see that here we've got the cos omega t surface and it's been modulated by this little function here, which is in effect e to the minus a minus t value. So it's going to decrease that surface as time continues. And whenever we integrate that from 0 to infinity, we're going to get some little function here. So it'll be a purely real part of the slice of the Laplace surface. So equally, we can take the e to the minus t times e to the minus 2t and modulate the minus I sin omega t surface, and you can see this being modulated here. And again, if we were to integrate in this direction, which is the t-axis, we would get the purely imaginary part of one slice of the Laplace surface. So you've got access to these files within the resources section. So right now we're going to have a look at the original function and we'll look at the cos surface that's been modulated by exponential and also the sine surface that's been modulated by the exponential. So the original function of time looks like this here. So that's a function of time and it's going to be modulated by one part of the e to the minus sigma t surface, and this gives us this function here. So we've seen that in a previous slide. So we can also go in and look at the cos omega t surface that's been modulated by the exponential, and this gives us our function here. So you can see that we have our cos omega t surface, but you can see the modulation here with the exponential, and that's the exponential modulation here. Now we can go ahead and we'll have a look at the sine surface as well. So this is the sine surface here, and again the sine surface has been modulated by the exponential, so you can see this exponential modulation here. So here's the final Laplace transform of the function that we've been looking at throughout this example. So we've got the Laplace transform of e to the minus t, which is equivalent to the Laplace transform of e to the minus 1 times t. So we've seen that the Laplace transform of that is going to be given by 1 upon s minus a. So that'll be 1 upon s minus, well in this case a is minus 1, so it's s minus minus 1, which will be 1 upon s plus 1. So then we say, where does the pole exist? Well, the pole exists whenever the denominator is equal to 0. So when s plus 1 equals 0, or that value is s equals minus 1. Okay, so it means that the pole exists, and the pole is a purely exists at a real value of minus 1. So it means that the j omega stays at 0 and the sigma moves to minus 1. So you can see that here, that this pole here exists at minus 1. So we can also look at the L1.m file, and if we were to put in our function here, which is 1 upon s plus 1, and we use the L1 in order to draw this function out. So when we draw it out, you'll see that we get the function in the complex frequency domain, and it's shifted by minus 1 in the sigma axis. So finally, let's have a little look at this e to the minus sigma t surface. So we've got t along this axis here, and the sigma is up this axis. So if we were to make the value for sigma equal to 0, then we would just have e to the 0, which is just 1, and this would give us this central black line here. So it would just be a little step function there of height 1. But if we were to make that value of sigma less than 0, then we would have minus sigma, which would be e to the plus sigma. So that would give us this end here of this function. So in this case, the function would start to diverge. It would start to head off to infinity. Now if we were to look at the value for sigma being a positive value, so it would be sigma would be e to the minus, and it would just be a positive value, so it would be e to the minus sigma t, which would be this side here, and it would start to converge. So you can see convergence here, and then a straight line of height 1, and then you'll see divergence. So let's go have a wee look at that live in Matlab. So finally, let's look at this exponential surface. Now the Matlab file, it's called matlab_exp_surface, which is in the resources section. Well, whenever you run that, you get the surface here. Now it's a wee bit easier to see in the Matlab than it is to imagine it. So you can see here that the value, whenever our value for sigma is at this side here, you can see that this function starts to tend towards 0, that is, it converges. And whenever it's actually equal to 0, it would just be a straight line here. So it would just be at a value of 1. And then for values in this side of the axis, you can see that it's starting to head away, so it's starting to diverge. So that gives you an indication of what the e to the minus sigma t surface is like for values of sigma ranging from positive 0 and negative values. So that's all there is for this video. The main conclusion is that we're able to position the pole anywhere along that sigma axis by that multiplication by e, the real exponential. So thank you for listening, and I'll get you in the next video. Goodbye.